Hello everyone, my name is Rema Wando. I'm presenting on behalf of our team, a team of two. We are Rema and Lillian, and our solution is having federated learning on Raspberry Edge Pi devices, and the model is going to do some soil-based crop recommendations. And we're fulfilling a task because uh, as globally the demand for food is increasing, so that demand has to be met. And by the way, one of the challenges is climate change, and the arable land is declining, and then also the soil health is declining. So one of the solutions is having data-driven agriculture, and this map shows how different studies that are being done in Africa about data-driven agriculture, where they involve sensors to have precision agriculture. So traditional approaches to this is that they have machine learning models that are being trained from data. So the nodes send data to the server so that the training continues. But then it's not practical when the internet is limited. And then as well as these devices are small, like Raspberry Pis, these devices are small in terms of memory and compute, so it becomes not that feasible. One of the solutions is having tiny machine learning models, compressing the models so that they fit into these devices. But when you want to have data like sensor data that is constantly being updated, then another solution is having federated learning, which is the center of our work. So federated learning is some form of machine learning where you have distributed training from training from distributed data, and this was introduced by Google in 2016. So the way we have our experimental setup, we use a publicly available data set, which has 7 features as different physical parameters measured from the soil. Then it's going to recommend which is the label, different types of crop depending on the physical and parameters of the soil. This is how we set up our experiment. We had 3 Raspberry Pis as client, then we have an Edge server, and then this is our algorithm. Basically, is that the global model is sent to the clients. The client trains the model, and then the weights or parameters of the model are sent back to the server. The server will do some aggregation, and then it will continue until the predetermined training ground is reached, is when the training stops. And this is the model. As you can see, it's not a pre-trained model. It's a very simple model that we used, and it has worked for our experiment. And this is just showing the results and how impact of the increasing the number of Raspberry Pis will affect the accuracy. And also we examined how epochs, when you vary the epochs and times on the time overhead, and also looking at computation as well as communication, which saw that up to between 1.5 to 1.9 gigabytes of memory is what is used. So this shows that the framework is running and is not affecting the other processes in the device because it hasn't even exceeded half of the Raspberry Pi memory. So, and we achieved the testing accuracy of 92, which has surpassed previous studies that were done using these Gaussian classifiers. So yeah, so in future, we are going to deploy it on the actual farms. And this is the work in progress. And then we are going to do further optimization in the model. These are some of the references, and thank you. And before that, I can show you part of the code in the server. So this is just to show part of the code in the server, how we define our variables, how the model, and how we do our communication. We initialize the communication between the server and the clients. And then this is just showing how when the clients are connected, training starts, and different data is transmitted to and from the server. And this is on the server side. And this is also what happens on the client side too, when model is being trained.